This video is on hypothesis testing, and we are going to determine what the null and alternative hypotheses are, the concept of type 1 and type 2 errors, and how we come up with conclusions to hypothesis tests. Mind you, this is a process to obtain a conclusion about a hypothesis. So we have an experiment or a study, and we make a claim about a parameter from the study, and we get a conclusion. And the process that is involved right here is hypothesis testing. Now you may wonder, well, why do I need to conduct a test? The importance here, or the importance that we place, is on sample variability. We've got to keep in mind about sample variability. Even though we have an experiment or a study that simply contains a sample, it is not a representation of the population. So if I went and collected a different sample, perhaps I could get a different conclusion. That in mind, we would like to say, well, if I'm going to make a conclusion, I have to put a probability on it and state, well, how likely is it that this conclusion is going to be valid from a statistical standpoint. We're not going to simply agree, rather we are going to say, with a certain probability, we agree with this conclusion, and there is room for error that we've got to keep in mind. So what is a hypothesis? Hypothesis is merely a statement regarding a population. And we don't make any arbitrary statement, we rather make a hypothesis about a parameter. So let's say we have a claim that the So the average age of individuals when they experience hair loss is greater than 50 is a hypothesis about people losing hair. And we are making a very specific claim about the average, and that is the parameter. And the claim is that the average age is greater than 50. Now, another example I could state would be the proportion So the proportion of males who experience hair loss is greater than 34.53%. So we're not making any random or any arbitrary claim. We are making a claim about a specific parameter, and that parameter here is the proportion of males who experience hair loss. And the claim made here is that it is greater than 34.53%. So that would be the parameter and that is the claim or the hypothesis. So this entire statement is a hypothesis that we are making, and we'd like to verify if that is true. And how do we verify? We collect a sample, we conduct a study, we follow through the steps involved in hypothesis testing, and we determine whether the claim is true or otherwise. So here are formal examples. So here is one. In 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes that this percentage is different today. So how could I phrase this? The researcher is claiming So in 2008, it was 62%. But what does the researcher believe today? The researcher believes that the percentage of American adults who regularly volunteered for charity work is not equal to 0.62 or 62%. So this is the researcher's belief. That is the hypothesis, and we're not going to blindly accept this statement. Rather, the researcher has to collect a sample, and based on the sample, we're going to conclude if the hypothesis is likely to be true or not. So here is another example. This goes back to the average. So according to a study published in March 2006, the mean length of a phone call on a cellular telephone was 3.25 minutes. A researcher believes that the mean length of call has increased since then. So how do we translate it in terms of a hypothesis? Mean is nothing but the average. So today's hypothesis is that the mean or the average length of a telephone call is greater than 3.25 minutes. So in 2006, it was 3.25 minutes. But since we are making this hypothesis today, we're going to state that it is greater than 3.25 minutes. Again, we're not going to blindly agree to this statement. Rather, we're going to collect a sample and verify the credibility of this hypothesis. And as I mentioned earlier today, hypothesis testing is a procedure, and it is going to make use of sample evidence, and the conclusions are going to be based on the probability. And whatever conclusion that we're going to make, it is going to be about the population parameter. So key things to keep in mind here is the claim or the hypothesis is about a parameter from a population, and the conclusion is a statement about the parameter pertaining to the claim that we just made. So what are the steps involved in hypothesis testing? Well, of course, the very first step is to make a statement regarding the nature of the population. In other words, make a claim about the parameter. The next step is to collect evidence, and evidence is simply sample data. And where does the data come from? The data is going to come from the population. So data and we analyze the data using what we call statistical tests. And we make a conclusion about the claim made for the parameter. So what is this process that we are talking about? The very first statement that we make about a parameter has a very natural definition. What is that definition? So we have something called H naught, or it is the null hypothesis. And this is more like the reference level for the parameter. For instance, as an example, I can say P equals 0.5. Here, P is the population proportion. Or I could state that mu equals 7.5. Mu is the population mean. So this initial statement is the null hypothesis. So, which is why we call it the statement of no change or no effect or no difference. And this statement is considered to be true until we find evidence which supports the counter argument. So since we call it, since it is a statement about no effect means null effect, hence the name null hypothesis. Null means zero. So the second portion of the claim statement is the alternative hypothesis. In other words, it is the counter argument toward which we are trying to find support. So let's go back to the previous example. Null is P equals 0.5. The counter argument would be P not equal to 0.5. So the null, it means there is no effect at all. The alternative is that there is some effect. In other words, we found evidence toward that statement P is not equal to 0.5. In a similar manner, the other example that I had was H naught, mu equals 7.5, and H1 is mu not equal to 7.5. So there are three different ways in which we could set up the null and the alternative hypothesis. Now, before I get into that, that entire statement, like we wrote, is what we call the definition of the hypothesis, or the initial statement of the parameter. And it has a very formal structure, so the definition contains the null part and the alternative part. So the first hypothesis type is the two-tailed test. So a two-tailed test is when we have the null is where a parameter is equal to some value versus the parameter not equal to some value. So what do I mean by that? So the first parameter that we can consider is the population proportion. So I could make an arbitrary claim that the proportion is equal to 0.5 against the proportion is not equal to 0.5. Now that is the first type, or the example of the first type, which is a two-tailed test. I could also make a claim about the population mean. This is an arbitrary example, so mu is equal to 8.4 versus the claim mu is not equal to 8.4. The second type is a left-tailed test. So a left-tailed test is one where the claim has less than in it. So if we look at this example, the alternative, which is usually or always the claim statement. So in the claim statement, we find a less than sign. So this is a left-tailed test. So as an example, I'm going to take proportion equal to 0.5 against proportion less than 0.5. So since we have less than, this would be a left-tailed test. So, all formally speaking, since the claim statement is less than 0.5, some might write this as P is greater than or equal to 0.5. So this part is the counter-argument to that part. And keep in mind, the alternative is the claim statement, or the claim statement is the alternative. So the other case would be to look at a greater than type. In other words, the claim statement has a greater than sign in it. Excuse me. So the parameter is greater than some value. As an example, I am going to consider the population mean. So I could say h0 mu equals 9.2 versus the alternative that mu is greater than 9.2. So that's one way of writing it. Some text would also go beyond and write it as, well, the counter argument to mu greater than 9.2 is mu less than or equal to 9.2. I myself consider the second type to be formal, and usually in advanced stats the second type is formal. So how could we put this into practice? So if we go back and think of the example from earlier today, someone looked at data from 2006 and made a claim today that the average length of a telephone call is greater than 3.25. So the null hypothesis is a statement about status quo, or no difference at all. In other words, we're going to keep what we believed in 2006 to be the same as today. The counter argument is that that is not the case. We believe that the average length of that telephone call, so the null is keeping things as is. The alternative is things have changed. But keep in mind, this is what we are claiming, and we have to verify this using a sample. And how do we verify this using a sample? We make use of the procedure called hypothesis testing. So here are cases. I believe I did this already. So percentage is simply proportion. So the belief since 2008 is that that proportion of adults, American adults, who volunteer their time for charity work, that would be P, is 0.62 or 62%. Today, the researcher is making a claim that it has increased and it has gone to, it's different from 0.62. Different in the sense it is not equal to 0.62. So if we don't find evidence to the claim made by the researcher, then nothing has changed. Everything remains the same. There is no effect whatsoever. So in 2008, it was 62%, and today the researcher went and collected data, and it still is 62%, in which case there is no support towards the alternative, which is the researcher's claim. So here is a case where the parameter is neither the mean nor the proportion. Rather, the parameter here is the standard deviation of the amount of wine put in a bottle and so that standard deviation, keep in mind, is a measure of variability. So if you recall, and the notation for population standard deviation is sigma. So what was the claim then? It was 0.23 ounces. So now that we have a new equipment, the quality control manager believes that this standard deviation has decreased, in the sense the parameter has gone down from 0.23 ounces to some other number. So that is the claim made by the quality control manager. So the claim is that the standard deviation sigma is less than 0.23 ounces. So that is the claim So if we do not find evidence toward the alternative, which is H1, we're simply going to say everything or nothing has changed because of this new equipment. There is no effect that was introduced due to this new equipment. So the standard deviation of variability is still 0.23 ounces. So if you think about it, we can recognize that the first case that we did here is a right tail test, or it would require a right tail test because of greater than sign. The second one here is a two-tail test, or it would require a two-tail test because of not equal to. And naturally, the third case here would be a left tail test. Because we have less than. So here is another case, which is the example where the average length of a phone call was 3.25 minutes, and the researcher believes that the mean length of a call has increased since then. So the status quo is 3.25, and the claim made by the researcher is that it has gone up from 3.25. So if you think about it, this would be an example of a right tail test because you have a greater sign. So I just wanted to take a look at what they're going over. We actually addressed this previously. So this goes back to the amount of wine put in a bottle, and the status quo, or the current measurement, is that it is equal to 0.23 ounces. Oh my. In other words, sigma is 0.23, and the alternative is that sigma is less than 0.23. So naturally, the test is a left tail test. So the alternative is the claim, and who's making the claim? The claim is made by the quality control manager. That is his new belief, or their new belief. So what are the four possible outcomes that one can expect? So we have the null, so the null is that the standard deviation is equal to 0.23, and we collect data to verify the quality control manager's assertion, and we end up rejecting the null. In other words, we are going to side with that argument. In other words, data is supporting the alternative. What if the truth, which we do not know about the population, the truth is the alternative? Then we are in agreement. In other words, the sample agrees with the truth. Keep in mind, the truth is unknown. We're just using this to explain the outcomes of hypothesis testing. So the truth is that the standard deviation is less than 0.23, and the data is also supporting the truth, so we do not make any error. Everything is peachy. Another case here so this is the claim made by the quality control manager. And we want to verify his claim, so we collect the data. And the conclusion is do not reject null. In other words, the data did not find any evidence toward the quality control manager's claim. It is pointing toward the null. What if the unknown truth actually is the statement in the null? Then we are in agreement with the unknown truth. So we made the right judgment, so we did not make a wrong decision. So no error was made. The next outcome is the null is 0.23, and or when the null is 0.23 and the alternative is sigma less than 0.23. Once again, that is the claim made by the quality control manager. So we collect data to verify this, and we end up rejecting the null. So we found evidence toward that. However, what if the truth that we are trying to find, that unknown truth, is actually not toward the null? Sorry, not toward the alternative. In other words, it is actually the null. So the data is pointing in the direction of the alternative, but the reality is that the null is true. So we made an incorrect decision, and this decision is what we call type 1 error. So is rejecting null when the null is true. And this is what we call, in other words, false positive. And the last case would be to have this scenario again. That is the claim made by the quality control manager. So we do not reject the null. In other words, we collect the data. The data tells us do not reject null. So the data is pointing toward the null. But what if the unknown truth is really the alternative? Then we made a mistake. The data is not discovering the truth properly. We made a mistake, and that mistake is what we call type 2 error. That is not rejecting null when h1, the alternative, is true. Keep in mind the concept of type 1, type 2 errors is quite abstract, and you just want to understand it for now. But if you encounter examples time and time again, you would get a better idea about it. So, in simple terms, this is what we call a false negative. In other words, we should have found an effect, but we ended up saying there was no effect. So it was a false negative. So for each of the following claims, explain what it would mean to make a type 1 error and what it would mean to make a type 2 error. So we don't have enough space here, so I'll do the first one here. So I'll just simply make a picture. So we write the null and the alternative, likewise the null and the alternative. So let's say that the truth is in the rows. The decision made by the test is in the columns. So if the truth is that there is no effect, it is status quo, 62% of American adults regularly volunteered their time for charity work, the test concludes the same, then there is no error. But if the truth is 0.62, but we end up saying that the proportion is not equal to 0.62, we found an effect when there was no effect to begin with. So that is type 1 error. So the truth in the second row is that there is an effect. Null is no effect, don't forget. So in reality, we should have found an effect, but we concluded that there is no effect. So that is type 2 error. And last case, the truth is that there is some effect, and our test clearly found that there is an effect. If that is the case, we did not make an error, so there is no error. Here is the second case. So the null here is that the average length of the telephone call is 3.25. Null means no effect. The alternative is not equal to 3.25. Oh, sorry. It's increased since, so this would be greater than 3.25. So that would mean true effect. So let's construct a table. Again, I'm going to consider that the truth is in the rows and the decision that we make from using the test is in the columns. So if the truth is that the mean is 3.25 and in reality it still remains to be 3.25, and that is our conclusion from the test, we made no error. But if the truth is that the mean length of a phone call is 3.25, but our statistical test ended up saying that it is greater than 3.25, we made an error, and that error is type 1 error. Next case, the truth is that we have an effect. In other words, the mean length of the telephone call is greater than 3.25, but we end up saying in our test that the average is the same, that there is no effect, but in reality there is an effect, so we made a mistake, and that error is type 2 error. And the last case is that in reality, the mean length of the telephone call or of a telephone call has increased from 3.25, and the conclusion that our test gives us, so that's our test decision, is also a mu greater than 3.25, then we made no error, hence there is no error here. So what we defined in the previous slides are simply the errors, the type of errors. We have type 1 error and type 2 error. So here we define alpha and beta. So these two are the probabilities of the error happening. So in other words, the probability of rejecting the null when the null is true is alpha, and not rejecting the null when the alternative is true is beta. So I have defined rejecting the null when the null is true. In other words, you're concluding that there is an effect when there is no effect in truth. So that is the type 1 error. Second case is the probability that you conclude that there is no effect when there is an effect. In both cases we make a mistake, so the probability of that mistake is alpha and beta. In other words, this is what we call as the false positive rate, and that is the false negative rate. So we can define alpha here as the probability rejecting that the proportion is equal to 0.62 when in reality the proportion is 0.62. So we are saying that this is true, or we found evidence toward that statement, but the truth is nothing has changed. and beta would be the probability not rejecting So if the truth is that the proportion of American adults who regularly volunteer their time for charity work is not equal to 0.62 or 62%, in other words, we should have rejected, or our test should have rejected the null and should have concluded that p is not equal to 0.62, but we ended up concluding, oh, we're not going to reject it. Everything is the same since 2008. Nothing has changed. So we made an error. So here, alpha would be the probability of rejecting the statement that the average length of a phone call is 2.5, when in reality, nothing has changed since 2006. In other words, the average length is still 3.25. So we are saying that it is not 3.25, but in reality, I'm sorry, it's not equal to, it's greater than. So we are saying, have it backwards. In other words, we are rejecting mu equals 3.25. We're saying that we found evidence toward mu greater than 3.25, but in reality, mu is 3.25. So the truth is that nothing has changed since 2006, but our test ends up concluding, oh, we found evidence toward the alternative. In other words, it's greater than 3.25. So we made an error. Beta would be the probability of not rejecting the statement if the truth is that since 2006, the mean length of a phone call has gone up from 3.25, and our statistical test ends up concluding, oh, that isn't the case, we'll simply say nothing has changed. Then we made an error, and that error is type 2 error. So the amount of type 1 error that we want to make in our conclusion is always chosen by the person who is conducting the research, and it is usually done before a sample is collected, and alpha has a very specific name. It is the level of significance. But it is also equal to the probability of type 1 error, which is the same as saying the probability of a false positive or false positive rate. And it is the same as saying probability of rejecting H naught when H naught is true, and it is the same as saying probability of well, I think I'll just stop there. Don't want to mention that statement here. So there is a perfect balance between type 1 error and type 2 error. So if the type 1 error increases, then the probability of type 2 error would decrease. If the type 2 error increases, the type 1 error would decrease. In other words, we can't have it all. At any given time, there is going to be one of these two errors occurring in our study, because again, the reason here is sample variability. We will be making a mistake for certain. The reason being, we are looking at random processes, random things, so there has to be variability. So we cannot establish a conclusion stating that, oh, we made no error whatsoever. There has to be some amount of error. So there is always this trade-off between type 1 error and type 2 error, and we have to watch out for which is more important in the study, and typically type 1 error is what we fix. So oftentimes students would say, oh, we don't accept the null hypothesis, or they would end up saying, we accept the null hypothesis. In other words, that would simply mean do not reject the null. From a logical perspective, that is the correct statement. Not accepting the null, or not saying that we accept the null hypothesis. So the null hypothesis is our reference value, and we cannot simply say what we chose as a reference to be true. In other words, we just accept our own reference. So that is something we shouldn't say. We always state our conclusion in one of two ways. We either reject the null, or we do not reject the null. So there is a very good example here. In our judicial system, we don't say that the defendant is innocent. We simply say we rather say that the defendant is not guilty. There is a complete distinction between the two. Good examples would be O.J. Simpson and Casey Anthony. So, according to a study published in March 2006, the mean length of a phone call on a cellular phone was 3.25 minutes. It's the same example that we'd been seeing multiple times. The researcher claims it has gone up since then. If the sample evidence indicates that the null hypothesis should not be rejected, the wording of the conclusion is, let's write the null and the alternative. The null is mu equals 3.25. The alternative is mu greater than 3.25. So our conclusion would simply be, do not reject null. And what is that null statement? Do not reject the statement that the mean length is 3.25. Suppose the sample evidence indicates that the null hypothesis should be rejected. here the conclusion would be reject the null, that is, mu is greater than 3.25. And here is a case when the sample evidence indicates that the null hypothesis should not be, I believe I copied that slide, so we're going to skip this. So a researcher obtains a random sample of 1,000 people and finds that 534 are in favor of banning cell phone use while driving, so p hat is 534 over 1,000. So p hat is what the sample gave us. Here is a very important question. Does this suggest that more than 50% of the people favor the policy? Or is it possible that the true proportion of registered voters who favor the policy is some proportion less than 0.5? And we just happen to survey a majority in favor of the policy. In other words, would it be unusual to obtain a sample proportion of 0.534 or higher from a population whose proportion is 0.5? We want to know what is convincing or statistically significant. So there are different scenarios that we can write here. The null is that the population proportion, in other words, P, it's missing in this statement, P would be the proportion of individuals in favor of banning cell phone use while driving. So the first case would be, is it possible that the true proportion of registered voters who favor the policy is some proportion less than 0.5? In other words, that would be a left tail test. But we could also ask the question, would it be unusual to obtain a sample proportion of 0.534 or higher from a population whose proportion is 0.5? So that case would be p equals 0.5, and the alternative is p greater than 0.5. So which is more appropriate? Of the two, the second is the test that we have to go with. Why? The sample proportion is telling us p hat is 0.3534. The important question is the one that is highlighted in blue. So just because we have 0.534, does it imply it is bigger than 0.5? So the way we translate that is 0.534 big enough to conclude that the true value of the proportion is greater than 0.5. Here is where the concept of statistical significance comes into play. Just because 0.534 is bigger than 0.5, we cannot conclude that the majority of voters are in favor of the policy. What is the reason for that? Again, sample variability. We are trying to make a statement about the population using a sample, and we have to account for that sample variability, because if I change its sample, it is likely I might get into or end up giving a different conclusion. So that said, the purpose of a hypothesis test is to answer this question. Is 0.534 truly big enough? In other words, is 0.534 significantly large enough to reject the statement p equals 0.5, that is, conclude that p is greater than 0.5. So that is the ultimate question that we want to ask in a hypothesis test, and the purpose is to determine significance, and which is why we call alpha the level of significance.